Good evening, everyone. So I will end today, but I would first like to tell you a little bit about how I came into nuclear medicine. So in June 2011, I was going to my first big congress in the United States, in Miami. And when you think about Miami, you think about the sun, the beach, the nice weather, the sea. But before getting there, you first have to go through border control. And for those who are familiar, in the United States, the border control people, the TSA agent, are not the friendliest people. And you don't answer questions if they're not asking, and you don't make jokes. So I was anxiously waiting in line to get into my turn, and I get in. It's my turn. And as the usual, fingerprints, picture, and the well-known question, what is the reason of your coming to the United States? So I answered, I'm coming for Congress. And the TSA agent asked, which Congress? And there I was quite hesitating, and timidly I mumbled, the Nuclear Medicine Congress. So the TSA agent looks up at me, and with a big smile says, oh, you mean the medicine that goes boom? And so I didn't know if I could laugh at the moment, but it was my first time with the general public idea of nuclear medicine, and it wouldn't be my last, as I continued working at the nuclear medicine department of the Jules Bordet Institute. And in our institute, what we do, we treat the big bad wolf that is cancer. So you heard already, but cancer has been cited as the #1 killer of the human species by Nobel Prize laureate Linus Pauling. And the World Health Organization reported that 1 out of 6 deaths in 2018 was due to cancer. And 90% of those deaths was due to the metastatic disease, so the spread of cancer over the whole body. And if you have disease over the whole body, you need a treatment that goes through the whole body. And there had been a lot of evolution in these treatments over the years, with going from a one-size-fits-all chemotherapy to targeted treatments that are individualized and personalized to a patient. And nuclear medicine actually offers a unique opportunity in these patient-tailored treatments. What we do in nuclear medicine is we give a drug, such as in the other departments, but our drug has a radioactive flag on it. So this is the uniqueness of nuclear medicine. And with this radioactive flag, we can do either diagnostic or therapy. But it's interesting is when you can use the same molecule for diagnostic and therapy, you get the radiotheranostic approach, where you use the same molecule for imaging and therapy. And in that, you are perfectly fitting the patient-tailored approach that now is in oncology. With that, you will give a radioactive payload to the tumor, and you can still detect it with imaging. A big advancement in that was actually the Nettle study that was published in 2017 in the New England Journal of Medicine. And for those who aren't familiar with this journal, it's like the Oscar, but in a journal format for the medicine. So very, very big impact. If you can publish there, you're gone. It's good. And the results showed that the same molecule that we talked earlier, the lutetium dotatate, this radioactive labeled hormone that is normally analog in the body, was compared to the treatment that is standardly given to patients, so the same hormone, but without the radioactivity. And you can clearly see there is a difference between the two. And the difference is actually really good because we have, for the patient receiving this drug, a slower progression of the disease, but also this was translated in a better overall survival. The patient lived longer with this radiotheranostic that is lutetium. So it was quite impressive. It showed great potential, and this was not missed by the different pharmaceutical companies that invested majorly in this radiotheranostic approach. And ourselves, Institut Jules Bordet, were major protagonists of this approach. We started launching this kind of treatment as premier in Belgium already. But we wanted to go bigger and better. And for that, we received financial support from the private sector. But as I said, we wanted to go bigger, so The well-known motto in Belgium is unity makes strength. So we collaborated. This is the basis what we do in Belgium. And the Brussels Radiotherapeutic platform was born. This platform was a pioneering collaboration for the development of molecular imaging, radiotherapeutic, and therapy. So before that, we had already a collaboration in Brussels that was called the Brussels Imaging Pharmacy. And it was a prelude to the BRTP, where 3 hospitals combined their efforts, UZ Brussels, Hôpital Erasme, and Institut Jules Bordet, to try to produce GMP PET radiotracers for the different centers. And this was the basis of the collaboration that we had with the BRTP. We work with the same people, but if you can see that there, instead of the UZ Brussels, we have the university. We collaborate with the university, the VUB. So it's VUB, Hôpital Erasme, and Institut Jules Bordet. And our main objective are to generate radiotherapeutic for the cancer treatments, and also to study and explore the fundamentals and applied aspects of radiobiology. So when we want to generate this radiotherapeutic, we have a lot of steps. First step is the design. Then comes the preclinical evaluation of this radiotherapeutic. Then the clinical production, and finally, where we want to get the ultimate goal, the clinical evaluation into our patients. So for the design, when you want to start with the design of a radiotherapeutic, you start with looking at what you want to target, the cancer cell. You want to get the cancer cell and not the healthy tissue. And so you select a target that is overexpressed on this cancer cell and that is appropriate for that. And against this target, you will generate a molecule that will be specific and recognize these targets. This phase, where we generate both, is called the concept phase, and is exactly the same phase that you have for targeted treatments in oncology. Our specialty is here with this radioactive flag, or the radiolabeling, and this is the uniqueness that we have with this radiotheranostics. Once we have the molecule that we want that is radiolabeled, it has to pass several quality controls to be sure that we have a molecule of high quality, to be sure that we can go further. And there we will look at the different physicochemical characteristics of this radiotherapeutic. But this doesn't tell us anything about the biological property of the therapeutic. We have to go to the preclinical evaluation for that. And there we will look at the fact if this molecule, after radiolabeling, still recognizes the target. This is very important because we want to get targeted treatment only to the tumor and not to the healthy tissue. So this information is quite crucial, but we want to look also at this radioactive payload that we will give. What is the effect of the radioactivity? And study the radiobiology of it, so to look at the radiosensitivity of cell, the radiotoxicity, and also the radioresistance. Today, the information that we have on radiobiology comes from external beam radiotherapy. So there has been a lot of research done on that, but very limited information is done on the radiobiology of radiotherapeutic, and this is where we want to study. And to understand and get the knowledge of that, we can work at different levels. We can work in vitro on cancer cell, overexpressing the targets. We can work in vivo in small animals, overexpressing the targets. And what we will get there is for the in vitro gain information about the binding capacity of our radiotherapeutic or internalization, the affinity and specificity for the targets. And in vivo, we will gain information about the distribution into the body of the small animal. We will gain information about the pharmacokinetic, the pharmacodynamic of our radiotherapeutic, and also the specificity and affinity inside the small animal. These small animals are generated either by modifying them genetically or by inoculating the same cancer cell into the animal, or even by taking a little piece of a tumor of a patient and grafting them on the animal. And then we get a patient-derived xenograft, a PDX model. But we can also, after giving this radiotheranostics, study it ex vivo. So we will dissect several organs and also the tumor and get information either on the heterogeneity of the uptake of a radiotheranostics in the organ or study different biomarkers of radiotheranostics in that. And once we are sure of the biological properties of a molecule, we can go further and try to upscale our production. And this we will do in the clinical production, where we can get the translation of a research and development production into the clinical production. And we will do it in a GMP fashion, following the good manufacturing practices. Here is an example of what we are now building in our new hospital that is being built in Op Campus Erasmus in Anderlecht. So there you have the plan, the layout of our lab. And you have here an image of how this clean room will look like. So we have different clean rooms. One will be for the development, the cold production, not radioactivity production of the molecule. And also 2 rooms will be dedicated on the radioactive part, one for the therapy, so for the thera part of the theranostic, and 1 room for the diagnostic part of the theranostic. But also, as I mentioned, we have to do quality control on the theranostic, and this will happen here. So now that we have a molecule that recognizes a target, that is radiolabeled, that we can produce with high quality, that has been tested, that it's biologically relevant, and we can produce this enough to get into patients, we get to patients. That's the idea. And that time, we want to get to patients, but first, before injecting the first patient, we have to submit a full dossier to the Federal Agency of Medicinal Products, the ethical committee, like other drugs, but because it's radioactive, we have to submit to the Federal Agency of Nuclear Control. So even for the drugs, we go also to the FANC, so that you know. And there, we finally get, if it's approved, we finally get to patients. And we will use the same molecule for the diagnostic and therapy, but just changing, as you can see here, the radioisotope. Gallium-68 for the diagnostic part and lutetium for the therapy. Here is an example that's what we have had with our patient in the Jules Bordet Institute. We started this in 2013. The first patient was injected with lutetium-128. And with this, we will have the same molecule injected with different radioisotope. We can do with the imaging a selection of patients, and also maybe try to predict the efficacy and toxicity of the treatment, which will help us to optimize the treatment to our individual patients. And what we have now is an approach where actually you see what you treat and treat what you see. This is fantastic for the patient-tailored approach. So also, for the clinical evaluation, we want to study the radiobiology of this radiotheranostics in patients. We are in a hospital, we have the samples of the patients, and what we will do is take biopsies, study biopsies of patients injected with this radiotheranostics. So tumor biopsies, but also liquid biopsies. Tumor biopsies are quite invasive. So liquid biopsy offers a non-invasive method, an alternative, that will not give us the whole information, but still can give us relevant information. And we can do serial liquid biopsies. So to resume, in oncology today, we try to do personalized medicine, individualized to a patient. In nuclear medicine, we have this unique approach that is the radiotheranostics approach, where we have 1 molecule that we can label with our isotope for either imaging or therapy. We will do it in the BRTP, and the BRTP will have 2 main objectives: the generation of innovative radiotheranostics, but also the study of the radiobiology of this radiotheranostics to try to find new relevant biomarkers that will give us information about radioresistance. And the goal is to have, in this state-of-the-art infrastructure, a network of scientists and clinicians that will work together to try to foster new exchanges and collaboration between these scientists and clinicians, but also between academia and industry. And our ultimate goal is to get this radiotheranostics to the forefront of oncological research to try to give a new approach for the patients. And so, if I would go back today to Miami and see this TSA agent, I will tell him that, no, nuclear medicine is not the medicine that goes boom, but it's certainly the medicine that is booming today. Thank you.